Okay, so let's continue from where we left over, right? So this time we try to look at chapter 10, the rapid oscillation under a rotating magnetic field. We have done a lot of math in the previous case, which is a linearly oscillating magnetic field. It is quite boring or difficult actually, right? And that's why I asked you to do in your assignment with sigma y, right? In another direction. I hope you can learn all those basic things. Now then, we will further here, we do one more things which is important. We don't use this often in spin qubit. It's not easy to make a rotating magnetic field on an IC chip. Or I don't know, maybe it's more difficult than linear oscillating. You will see later, all those papers, they use linearly oscillating magnetic field. It's easy just to pass an AC current on a wire, then you have this linear oscillating magnetic field. But the concept we learn here will be useful for superconducting qubit later. We come up with something called effective rapid frequency and the angular momentum vector on the broad sphere. So I have all the math, but as I said, I type them, right, instead of writing here to save the time. I hope that you can go through, right? If not, it doesn't, I'm not going to test it, right? But I'm going to test the concept. This is for final, right? Not for midterm. So let's go back. What did we learn? This is also very important about quantum gate. What is quantum gate? This is an important concept, right? We say, we try to solve the Schrödinger equation. And after all, the Schrödinger equation should give us how the new state of the, how the new state is related to the initial state. And it is multiplied by a matrix. Although this is complicated, but after all, it is just a matrix, right? And this matrix will be the quantum gate. So no matter what we are doing, our goal is to find out an Hamiltonian, which is the energy landscape, such that e to the power of this Hamiltonian divided by RH bar times t will give the desired quantum gate that we want. So for example, we actually learned that before, like for Lamarck precession. We say that, okay, in Lamarck precession, the Hamiltonian, right, you go through the derivation we learned earlier. What is Lamarck precession? It is magnetic field pointing downward in this case, and then you split the energy into two parts, right? 0 or spin up, and 1 spin down. This is for electron. And do you remember when the spin is, well, it is a negative charge, the magnetic moment is opposite or aligned in parallel, anti-parallel or parallel with the magnetic moment. I forgot what I was asking. Between the spin is parallel or anti-parallel to the magnetic moment when it is negative charge. We're going to have exam in 2 days, right? No problem, you have cheat sheet, right? So you know that you should put that down. Right? In real life, you know that it depends on charge. At least you know that you need to ask ChatGPT, right? So this is what is important, right? So negative, the way I memorize is negative opposite, right? So it is opposite, right? And then you remember the Hamiltonian between the magnetic field and the magnetic moment is what? H equal to negative mu dot B, right? So when they are parallel, then you have lower energy. When they're anti-parallel, you have higher energy, right? And then when you go to spin, then further negation. And that's why when you spin up and then you are in the opposite direction, it means the magnetic moment is in the same direction. That's why you have a lower energy, right? But you don't need to go through this all the time, right? I will memorize this figure because now I just remember it's pointing down, then I have the top 0, the bottom is 1, and it's electron. Then if you ask me how, I know that it's going to swap, and then if the magnetic field goes up, then you will swap again. Right? That's how I memorize it. But anyway, this Hamiltonian give me this, and we learned something called Lamarck precession. It has a Larmor frequency, which depends on the external magnetic field and E divided by M, right? What is E divided by M, by the way? Is the gyro, is approximately equal to the gyromagnetic ratio, right? Which is G E divided by 2M. Right? If you don't have electron, then you need to plug in the correct G. Proton was like 5 point something. The reason I can cancel G and 2 is because G is approximately negative 2.002 something, right? For electron. Right? So you see that Larmor frequency is important, right? So anyway, we plug in this H0, then we get the gate. So basically, this is just a phase shift gate. We plug into the equation, right? Then we know how it will change. You might not be able to memorize what is the expression of the state in terms of the polar and azimuthal angle, but you should be able to study and write in your cheat sheet, right? These are basic things, right? Any questions? So after all these words, is to remind you what is Larmor frequency, but most importantly, how the quantum gate is related to Hamiltonian. Okay, any questions? Okay, if no, then let's go back to this rapid oscillation. Again, it would be good you can kind of remember the procedure. Right? Memorizing is, like people say, not very useful in education, but sometimes you need something handy in your brain to do further reasoning, right? You cannot always check something or look at ChatGPT to get the basic thing. You do need to know something in order to have a faster reasoning. So we have gone through this. Maybe this is equivalently the third time. The first time is Larmor precession. Second time is the rapid oscillation with the linearly oscillating magnetic field. And now it's rapid oscillation with the rotating magnetic field. So again, we have the external magnetic field pointing down, DC, pretty large. Why we need this magnetic field again? What is the effect of this DC field? Zeeman splitting, right? It tries to cause the splitting of energy. So spin up and spin down have different energy, right? And then we have this rotating magnetic field. You look at this is really rotating. So it means the vector, the real 3D vector is just pointing around for 360 degrees, right? Keep going. And with an angular frequency of omega 1. Okay, how to generate this magnetic field is another thing. We don't care now. We assume that we have this magnetic field. And we can express this as this. We did not go into the details. You just do this, right? Start with time equals 0 and then delta t. You will find that it's indeed rotating clockwise when you look from the top. Okay. So we have this magnetic field, which is a vector. Then we remember the total magnetic field. You need to add the external magnetic, the DC magnetic field. And this is just a vector, x, y, z component. So we set up what is the magnetic field, and then we need to set up the Hamiltonian. This is step 2. Maybe I can label it, right? This is step 1. This is step 2, right? Of course, I'm not going to test the step, right? But I think you should be familiar with the process. Find the Hamiltonian. Because I know that if I can find the Hamiltonian, all I need just to do this exponentiation, I will know how it evolves. You might not be able to solve it, but numerically, you actually can use a computer to solve it for you. Then you don't need to do anything. But in class, we do this to gain insight, so we need analytical solution. And again, Hamiltonian is, here I just say mu dot B, right? But in reality, if you go to this complicated system, it should be the angular momentum operator dot the magnetic field, okay? And then, again, this introduced the Pauli vector. And I hope you are very familiar with this notation for Pauli vector. You should be very familiar with x, sigma x, sigma y, sigma z. And you should also remember that when we say sigma 0, sigma 1, sigma 2, sigma 3, what are they referring to? What is sigma 0? I. Sigma 1, sigma x, sigma 2, y, sigma c, right? They're just different label. And you should know the matrix, right? If you don't know what you do, just put on the cheat sheet, right? This is a basic thing, right? So this is the poly matrix. And then, yeah, you just go through the regular vector product, although this is not a 3D real space vector because it has the matrix as the coefficient, right? But still, you just go through the dot product as it is. Then eventually, we come up with this Hamiltonian. Again, we have the H0 due to the DC magnetic field doing the splitting. And then we have this HI, right? You can make it large this time, no problem. But particularly, we introduce a quantity called Rabi oscillation in this setup, which is EB over EB perpendicular over M. And for those who already study, you should know that, hey, this looks like this Lamarck precession frequency also, right? B0E over M. And then later I will show you, indeed, it is Lamarck precession if you go into the rotating frame. We discussed this earlier already. But the point is that you should understand any rotation depends on the magnetic field and also the gyromagnetic ratio. Right? Also, we have many things, but if I'm sure you'll forget everything, right, after this class. But I hope that you have this imprinted in your mind, just like F equal to ma, right? You probably forgot lots of stuff you learned in high school for mechanics, but you can say F equal to ma, just like this, right? Okay, that's the first thing, right? So we don't need to go through the derivation, they're just math. Then we will do some math, and here is one skill that we will use commonly in this quantum computing or this atomic physics or whatever. We introduce a variable called sigma plus and sigma minus. Now here actually I was not clear. This sigma plus is proportional. This symbol is proportional. I hope that you understand proportional. It's not really the lowering and raising operator, but this is proportional. I hope you can take a look at my book. I have a link to the exercise to discuss the real lowering and raising operator. But doesn't matter. But this is the confusing part because when you read the literature, sometimes they use another definition for sigma plus. Sometimes they have sigma plus at the bottom. We'll introduce that one later, right? I will also explain more later for them. But whenever you see this, you need to be careful what they are talking about for this sigma plus, right? They have different definition, but very similar, okay? So with sigma plus is sigma x plus I sigma y, sigma minus is sigma x minus I sigma y. So you go through the math, then you will get this. And then you can represent sigma x and sigma y as this, right? So you should know how to do this matrix operation, right? Addition of matrix or whatever, if I ask you to do that. So what did we do? We still have this hi equal to something times sigma x and something times plus something times sigma y due to this oscillating magnetic field interacting with the, okay, connection is not stable. Oscillating magnetic field interacting with the spin, the magnetic moment. Right. So what we did is just substitute sigma x sigma y by this, and then we have a lot of math, right? By recognizing we group the sigma plus together, and then use trigonometric identity, and then you come up with these two terms. Any questions? Right. Yeah, and it's difficult for you to memorize because, yeah. Which one? Raising and lowering operator. The physical significance is this. It actually will change the state of the state from one eigen vector of sigma z to another eigenvector. Yeah, so this is a little bit confusing, right? I will just verbally say that. So sigma z, you have two eigenvalues, -1 and +1. Here is confusing part. Here the raising operator, right, will only proportional, is to raise it from one state to another state where the state has a higher eigenvalue. So raise from the state of eigenvalue with -1 to eigenvalue of +1 in this definition. Okay, so that's what the raising and lowering means. Okay. Or in other hand, then you can think about it is like changing from spin up to spin down and spin down to spin up. Okay, so with this, then we try to solve, right? You have the HR, you have H0, then I should be able to solve it. Yeah, you can do it numerically, but now we are trying to solve it from another view. Let me see. Look at my cheat sheet. Yeah, so last time we say that, again, it's difficult, so I only give you the answer. First, we want to transform it into the rotating frame of omega 1. So what is omega 1? The field is rotating, right? Just now I said I'm standing on the ground, merry-go-round is rotating. So what I'm going to do is I run together with omega 1. Then omega 1 will always pointing at me, right? So it becomes a constant field. And that's why I want to work in the rotating frame. And if I do so, right, I need to do the transformation of the frame. How do I do the transformation? The transformation of rotating about z-axis is given by this. URF equal to e to the power negative I omega 1t over 2 sigma c. Very long, I don't need you to memorize. You can take a look at the chapter, how we came up with this form as one way, right? But after all, you have this transformation matrix, then originally, this one means that this is state, right? This is the state in the lab frame, right? For example, you are in the laboratory, you observe this state. After transformation, this one is the state in the rotating. Right? Is this okay? For example, like what I said earlier, merry-go-round. When I look at the states of the kid on the merry-go-round, when I was on the left frame, I saw that it's a very complicated curve going up and down and rotating, right? So that is the state. Now I jump on the merry-go-round, I actually only see that kid is going up and down. Let's say it's very simple, only up and down. He or she is not rotating, right? We have the same distance forever because I'm on merry-go-round. So the state will be different, but how do I transform that state to this state? I just multiply by this matrix, right? And how do we get this matrix? I don't go into detail. You can read just one page, some explanation. Now, same here. This is the operator. It is the same, right, for operator. So think about, let me say, okay, now I want to throw a stone, or not stone, let's say throw a toy to that kid, right, because that kid well behaved, I want to throw a toy to that kid. My operation on the floor is maybe, I need to have a very complicated operation in order to have that toy reach the kid, right? So it might be, that is the operation. Operator on the left frame, right? But if I jump on the merry-go-round, I will see that it's a very simple movement because I will see that it is just going in a straight line to that kid, for example, right? And how do I transform that complicated curve into that straight line mathematically? It is through this transformation. So this one you can try to memorize it. Again, this is not a part of the midterm, right? But I want you to appreciate this. Okay? And the reason I do this is because I want to prepare myself to solve the Schrödinger equation. Now, if I jump on the rotating frame, everything is rotating, then I follow the Schrödinger equation. The rate of change of the state in the rotating frame proportional to the Hamiltonian times the state, right? So if I was on the ground, then I will use this equation. And now the problem is that how do I solve this equation? Right? So here I just want to introduce a way, right? How do I find out what is HRF? Now, this was something confused to me. I always make mistake when I learn this. I thought that, oh, this is Hamiltonian. Isn't that I just need to multiply Hamiltonian by URF and URF dagger? But no, this is talking about operator. Hamiltonian is not the operator. It's not the gate. Remember this? Hamiltonian is actually, the gate is actually equal to e to the power h. Okay, so you transform the operator, but you don't transform all matrix in the Schrödinger equation. So this one you need to be careful. So I cannot just say that HRF equals to URF times H times URF dagger, right? So let me make this very clear. I can definitely warning, right? HRF is not equal to URF times H times URF dagger. Okay, so you cannot do this. So how do I transform this? So this is what I'm going to do. So let's do this step by step. First of all, in the left-hand side, I have I H bar partial psi RF divided by partial T. Correct? This is the left-hand side, sorry, right? So what is this in terms of the original psi? It's just equal to URF psi partial T, right? I just substitute this one because the state will become this. So I substitute U psi RF as URF times psi. And then I just apply the rule of differentiation. I get I H bar. I first differentiate the first quantity. So it is partial URF, although this is a matrix. I will differentiate this first, and then I keep the second quantity unchanged. And then I keep the first unchanged, and then differentiate the second one. Can you follow? No? This is a product, right? I do a partial differentiation on this product. Then I will differentiate the first term first. Second term, keep it as it is. And then keep the first term, and then differentiate the second term. You will see this very often in the paper so it is good to practice, right? This is again talking about partial AB, partial T equals to partial A, partial TB plus A, partial B, partial T. Make sense now? Yeah. Why would it time dependent? Let's look at this example. Indeed, it's time dependent. So the transformation actually turned out to be, because it's rotating, I will keep up with it, right? In that sense. Yeah. Yeah, how long it has been rotating, something like that. Yeah, so you cannot assume it is constant, the URF. Yeah. So it's time dependence in general, right? So this is one way to do it. Now then with this, what do I do? Then, now you see this also equals to, just look at my cheat sheet. This also equals to I H bar partial URF partial T. It is the same, I keep it. But for the second term, this is just URF times H psi. Do you know why? because I keep URF here, this is I H bar partial T partial psi partial T, right? This is the Schrodinger equation on the lab frame, right? So this one give me H psi. The reason I do it is because I already know what I'm doing, because I want to relate, I want to get this one. Is this okay? I just substitute, right? This is from here. Okay? Then I continue. I also know that, what should I put? I just continue on this. This is equals to, maybe it's better to put it here. This is, so I continue. This is equal to I H bar partial, I just copy this one, URF partial T. And then I want to represent this in terms of URF. I mean psi RF. So this is maybe confusing. Now I want to represent this psi as a function of psi RF. But I know that psi RF psi becomes in the rotating frame, right? Maybe this one I should also give the name. I will call this psi RF. Okay, and this is MRF. That might be, then you won't get confused. Right, this is just the operator in the rotating frame. So psi RF equal to URF times psi, right? Then this is a basic thing. How about psi in terms of psi RF? What do you get? How do you get it? URF times psi equal to psi RF. Then psi equal to what times psi RF? URF dagger. So if you still don't know what we are talking about, you really should study this part, okay? Psi RF psi equal to psi, URF psi equal to psi RF, right? I multiply this by URF dagger, URF psi equals to URF dagger psi RF. Is this okay? I just multiply psi RF, URF dagger to both sides. What is this? Identity. Why? What do we call this? Unitary matrix. So this is a hint. You probably should know what is Hermitian matrix, what is unitary matrix. Right? These are the basic thing, right? And why this is unitary? Because this is just a gate operator. We know all quantum gates need to be unitary. Okay? So that's why now I put psi equal to URF dagger times psi RF, right? Then I further do the same thing for the second term. I get, this is confusing, URF H URF dagger psi RF. Right? I just substitute this psi by the same thing. Okay. And maybe I should have done that even earlier. Let me just group it. This is your IH bar, partial URF, partial T, and then URF dagger plus URF H URF dagger, the whole thing times psi RF. What I'm doing is just to factorize psi RF. So I have two terms, both of them as psi RF. I take it out, and then I just group this operator together. But what did we say? We say this one is just equal to HRF times psi RF. From here. right? Because this term equal to 7, right? This is just equal to right hand side, right? So what I have done is just to show you that HRF equal to this complicated term. So HRF is not just HRF, HURF dagger. It also includes this term. And it is equal to this term if actually URF is not time dependent. Then this will be 0. Now, you don't need to memorize this, but the most important thing in this slide is to tell you that when you do transformation in the future, do not take it for granted. You need to be careful about whether it's time dependent or not. Right? And then all this math skill, you should be able to use it, understand it. Any questions? So don't worry too much, right? This is not in the midterm. So this is something new. But this skill is important. Or more importantly is the awareness of how to transform the Schrodinger equation into a rotating frame. Right? And understand like what he just asked, why URF is time dependent. It is given as time dependent. Then you have this term. Any questions? Now, if no, then what do we have? We have this HRF, right? And then this was the original Hamiltonian, right? So in that case, I need to plug in this one to here. And then, because this is this one, so I actually need to, sorry, I should say again, I should plug in this H to here. Very lengthy, right? So that's why I don't want to write it. I plug in this to here to get HRF. And of course, it's very complicated. First, I need to compute this term. I already know what is URF. I just go through the differentiation. No worry about the step. If you're interested, it's good you know the step, but important thing is here. This term gives us H bar omega 1 divided by 2 sigma C. Very similar to the Hamiltonian of H omega L divided by 2 sigma C, which is negative, but here is positive. But it gives this term. When I plug in the second term, you go through all the math again, you have this complicated thing, right? So let's look at the second term. Is it okay? You see this second term was like I plug in this whole H, right? So I plug in the whole thing into here. So I have URF dagger, and then just copy this whole term. And what I need to evaluate is URF sigma C, URF dagger, URF sigma minus URF dagger, URF sigma plus URF dagger. You actually can calculate it yourself using matrix. Right? You can check my book. But more importantly is usually people just check the table. So there are two things. The sigma plus is transformed like this. It becomes still sigma plus, but we have an extra phase depending on omega 1. Sigma minus has an extra phase, also depends on omega 1. Do you know what is this, by the way? Maybe I should explain a little bit more, right? This one just gives you sigma z. I don't need to calculate it. Why is that? Because URF, as I showed you earlier, equals to e to the power negative I omega 1 divided by 2, what's that? Sigma c t, right? Let's check if this is correct. Right? Negative 1 omega 1 t divided by 2 sigma z. This is diagonal. And you have this one multiplied sigma c. They have, if you explain Taylor expansion or look at it as a diagonal matrix, they commute with each other. So that's why URF sigma z URF dagger equals to URF dagger sigma z. They commute. So sigma z times URF dagger just equal to URF dagger sigma z. And what is URF times URF dagger? I again because it is a unitary matrix, right? So that's why we get this one. Right? So we don't go to the math, but you see that this process gives me a term that is h bar omega 1 divided by 2 sigma c. One term is negative h bar omega L divided by 2 sigma z. So they can be grouped together. And then I have these two terms, sigma plus and sigma minus, right? So that's how I get it. I have omega L minus omega 1. And this is an important concept which we discussed earlier again. It always depends on the content, but they are all called detuning. This is another detuning. Remember the detuning we did in the linear oscillating magnetic field? It was the frequency difference between omega 1, how fast the angular frequency oscillates, compared to normal precession. Here the detuning is what? It is the difference between the normal precession frequency and the rotating magnetic field frequency. So in almost every problem, you will see this detuning, and they are very important. You use detuning to do some interesting physics. And so up to this step, I don't require you to be able to derive this, but I hope you realize that because of this derivation, we come up with something called detuning, the difference between the normal frequency. Normal frequency, let me emphasize again, is the characteristic frequency of the system. The qubit has two levels, and its precession frequency is proportional to its energy difference, right? So that is you can think about as maybe the resonance frequency of the bridge, right? And omega 1 is a perturbation, or in this case, a real force that applies to this bridge. So the difference between these two frequencies is the detuning. And you can imagine when you have zero detuning, you will get into resonance. Think in this way, that way. Is that okay? Right, so I hope that now you have a concept is that whenever you see a spin qubit, but the same apply to other qubit, the concept, they have a characteristic frequency. That is the normal frequency. Because that is proportional to the energy difference between these two states, 0 and 1. And remember the differential criteria? And you should know what is differential criteria, right? Another hint. Remember the 5 criteria. One is that you have a well-separated qubit. Well-separated and well-defined two-level state, right? And that's why it's so important. That's one thing. Another thing is now I have sigma plus, right? So I decided to go here and plot back the sigma plus as sigma x plus I sigma y, sigma x minus I sigma y. Then I go through the math. I come up with the final Hamiltonian in the rotating frame. Remember, this is in the rotating frame already. Right, so I'm already on the merry-go-around, okay? And what I see is that I see the Hamiltonian is just like the Pauli vector dot product with the effective external magnetic field. When on the rotating frame. Do you see this? Let's go back one more time. Again, how we find the Hamiltonian? We always find Hamiltonian using this equation. And it always gives us a constant in front, the Pauli vector dot product with an external magnetic field. That is the physics. It's always Pauli vector dot product of the external magnetic field, right? I did all this complicated transformation. Fine, I forgot, it's difficult. But finally, I see that on the rotating frame, I get this expression. Isn't that is also a Pauli vector dot product with a column? So I can call this the effective magnetic field, right? Because in reality, if I really have this magnetic field, then I will have this Hamiltonian. Make sense? So this one gives us an effective magnetic field. Now, but this is not real magnetic field because of the unit, right? Because I should have E over M or a gyromagnetic ratio here, then it will be the magnetic field, right? So, but anyway, it's a sigma dot this guy, omega R, okay? And what is omega R? Right, so this is, look at this is just like what? H bar omega L sigma Z. Think about this in DC field, right? Can you tell me what happened when you have this Hamiltonian? What happened to the qubit when you have this Hamiltonian? Precession. Let's step back if you forgot. How we get this Hamiltonian? How we get this Hamiltonian at the very beginning? Because of the DC magnetic field. And he said precession. How does it precess? How does the qubit precess when we have a DC magnetic field? You use right-hand rule, right? Am I right? When you're pointing down, you use right-hand rule. Then it will rotate clockwise when we look from the top, right? That is the precession. So you precess about the DC field. Here I have the same Hamiltonian. If I treat this as a magnetic field because it has the same direction, then it means I'm going to precess about omega R. Omega R is a vector of this form. This is important, right? I'm reviewing also for midterm. Of course, we are not testing this, then it means I might be testing this, right? So you need to make sure that you understand. Oh, direct. I mean constant. Let's just call it constant magnetic field. Direct current, but so in electrical engineering, it kind of messed up, right? Direct constant means constant. Yeah, direct current means constant, but here it's not current actually, right? Like AC, we see AC magnetic field is not a current either, but we say AC magnetic field. Yeah. So this is confusing, but it means constant in magnitude and also direction. Yeah. Good question. Yeah, I don't have the picture, but do you understand what I'm talking about? And this one you definitely need to study, right? Again, I say that if you have what is that? B equals to negative B0 Z hat, yeah? Then your qubit is going to precess at omega L. Equals to E over M, or I will go directly to the number of, oh no, this is also already right. E over M B0. Right? You should know this equation. Correct? Right? The form are all the same. And again, the world is isotropic. If the magnetic field is pointing down, I use my right-hand rule, then the state will rotate about that magnetic field. Then it's pointing to the left, then I still use my right-hand rule, then you rotate about that magnetic field, right? That should make sense, right? And that is exactly what I'm trying to say. Recall, oh, I actually have this here. You have the magnetic field pointing down. You get this Hamiltonian. At the beginning, it was very simple because we only have a DC magnetic field, constant magnetic field, right? So, but still we can write this as this. Sigma X, sigma Y, sigma C, dot product 0, 0, negative omega 1. This is the same as this. You should know how to do dot product. Make sense? And we know it's precessing like this, right? This one you need to go back to study. And we have this angular velocity vector. So maybe I should talk about the name, right? So I would just emphasize that omega R is the angular velocity vector. For those who still remember from your physics, rigid body rotation, right? This was just the angular velocity vector. Right? If you rotate in this way, use your right hand rule, you're pointing up. And this is proportional to the angular momentum, right? You multiply this by the what? Inertia. Not inertia, moment. Moment, right? Moment of the, instead of multiply the mass, you multiply the moment of the system. Then you get the angular momentum. In mechanics, I forgot all the terms, sorry. Yeah. Okay, but don't worry about this. What I'm trying to do is now you have this form. This form are exactly the same. But now this point is pointing at different direction depending on omega r and phi b. Okay? So what does it mean? What is phi b? Do you remember? If you forgot, let's look at the figure again. The equation again. What is phi b? It's just the initial phase of your rotating magnetic field. So whether you start from this angle or that angle, right? Again, what is omega r? Right, this is initial phase. And what is omega r? The capital one. Omega r equals to E over m times b perpendicular. Right? Just like Lamarck precession. So it means if I change the initial phase, this is very important. That's why electrical engineer microwave is so important. Well, not here, right? Because we're talking about magnetic field, but later on superconducting qubit or spin qubit, you try to control using current. This phase is going to determine the direction of this vector. If it's pointing down, then your qubit will precess here. It's pointing in this direction, it will precess about this vector. Right? And what is delta? Do you remember? What's the name for delta? Detuning. And it's the difference between omega 1 and the normal frequency. So what does it mean? If I change, if delta equal to 0, this is for ZS's, right? Then it means this vector is on this plane, right? But anyway, I can tune this vector so that I can bring my qubit from any position to any position. Right? Because I just put the vector in the right location, then the qubit will just rotate about that vector. And do you still remember how we do the rotation? Another hint for midterm, right? How do we implement the gate? A general gate? You will do free Euler rotation. Remember? Rotate about z-axis, rotate about y-axis, rotate about z-axis, right? Here is not exact. I still talk about rotate about z-axis, but we usually don't do that. But how about let's think about y and x-axis. You just need two axes to do this Euler rotation. So I will be easily to do a rotation about x-axis and rotation about y-axis. Correct? By just changing the phase. And I even don't need to change the magnetic field. That makes the design very easy. I don't need to change my magnetic system. All I need to do is just change the initial phase because cosine phi b, sin phi b will cover from 0 to 1. Then it allows me to put this vector in any location on this equatorial plane. Right, so I know a lot of math, but after this, these are the most important things you need to memorize and appreciate. Because no one will ask you to derive this. No one will appreciate, right? But the understanding of its physics is very important. So that concludes the, and we did not solve this, right? If you, this here, how do we solve it? We just try to do an analogy to the Lamarck precession. Right? Because it's very difficult to solve. But if we solve it, you will get what I'm saying. Okay, so now this is an important concept. Later in superconducting qubit, we'll come back again. We will come up with some effective magnetic field again, although there's no magnetic field. And you will see how you change the state of a superconducting qubit. Okay, so that's it. And then we go to another topic. And any questions? Yeah.
Yeah, so here if the detuning is very high, that means it will be resisting
yeah, so you see that we really cannot rely on detuning, right? Because you need to make this really high in order, and then this very small in order to have vertical, right? But usually we actually do not need this. We just we don't need the rotation above z-axis. We just transform the coordinate system when we do the computation. So that is called virtual z-gate. Okay, so you can just make detuning equal to 0, so it is in resonance. Then you will have this vector always on this plane. But again, you rely on x and yz to do the free Euler rotation. Then you can rotate from any point to any point. Yeah, but theoretically, yeah, you see that I cannot make these two both equal to 0 at the same time. Then it means in order to have z-axis, I need to have delta equal to infinity, right? But that is impossible. Okay, good question, yeah. Okay, then let's look at the implementation, right? So on chapters 11 and 12. Okay, another hint. So let's recall from now, how do we implement semiconductor qubit? Oh, sorry, I actually need to introduce a concept. I forgot to say that. Now then, the real frequency that is oscillating, right? The real frequency that it is oscillating, we define something called omega dash, this is a scalar, equals to the magnitude of this vector. And of course, the magnitude of this vector equal to omega r squared plus delta squared, right? Because omega r squared, this is something here, right? Omega r squared is just omega, this is x squared plus y squared plus z squared, right? So x squared plus y squared, this term actually cosine squared plus sine squared equal to 1. So I have omega r squared and plus this delta squared. Just trying to say that if your detuning is not 0, your effective rapid frequency, I think it's called generalized, I forgot the name. I think it's the generalized rapid frequency. Generalized rapid frequency. That is what you really get from experiment. It's not the rapid frequency, omega r. Right? It's not E over m times b perpendicular. It is equal to this. Okay. Yeah, sorry for